Thank you very much for giving me the opportunity to talk about my research at Amplitudes. So today we'll talk about understanding some supergravity theories with reduced supersymmetry, specifically n equal to supersymmetry in 4 and 5 space-time dimensions, as double copies of these theories. And I should mention this is work done in collaboration with Murat, Henrik, and Radu. So my starting point will be this double copy construction with Bernker, Asper, and Johansson. I will review this only very briefly, as Alex has already spent quite a bit discussing the construction. So the construction is based on the availability of gauge theory amplitudes in a form in which numerator and color factors, which again a diagrammatic presentation of the amplitude, obey a duality known as color kinematics duality, in the sense that whenever you can find the 3 color factors which add up to 0 for 3 graphs, you have that the corresponding algebraic relation is also obeyed by the numerator factors. Now, once presentation of an amplitude with this property for gauge theory are available, then you can obtain straightforwardly at loop level, also at loop level, I should say, the amplitude of a gravitational theory by replacing color factor with second copy of the numerator factors, which can also come from a different theory. They do not necessarily need to come from the same gauge theory. So a couple of comments are in order here. So this construction has been critical in making possible multi-loop computation for supergravities with maximal and half-maximal supersymmetries, which would have been undreamed of maybe 10-15 years ago. But also, aside from computational efficiency, these constructions, in a sense, are at the intersection of many interesting ideas or recent research directions, ranging from string amplitudes to scattering equations, ambitwistor string, classical double copies. At this point, the double copy property has been established, mostly on a case-by-case basis, for very large classes of gravitational theories. The starting point for you were supergravities with a large amount of supersymmetries. This was the first one for which the property was established, but also onward from there would be several extensions. Alex has reviewed some of these, so I will not repeat here. But what I want to say is that essentially the fact that this double copy keeps being established for larger and larger classes of theories essentially prompts a question, which is this a lucky accident, or a collection of more and more lucky accidents, or is this a property, for more or less general property of gravitational interactions? If you want to answer in the affirmative to this question, then you must be able to do the following. You must be able to walk to your favorite supergravity book, open a page, pick up a random theory from there, and then turn your knobs, pull your levers, and come up with 2 gauge theories, which are just the right gauge theories to reproduce the amplitude of said supergravity theory. Not only that, but whenever you read a statement about that gravity, for example, that gravity may have an isometry group or some symmetry, then you must be able to deconstruct that structure in terms of structure which appear already at the level of the gauge theories. Okay, having said that, this is what we would very much like to be able to do. I want to restrict myself to theories with n equal to 2 supersymmetry. There are a couple of reasons to do so. First of all, these theories are in a sense a natural testing ground for ideas about more general gravitational theories, in the sense that n equal to 2 supersymmetries is a reduced supersymmetry, so the theories already show some of the features of generic gravitational theories, because supersymmetry is not as constraining as in the more supersymmetric relative of these theories. But also, you have that you have just enough supersymmetry left that the situation is still under control. Also, it should be mentioned, if you care about unique properties of gravitational theories, that divergences in theories with reduced supersymmetry with matters are expected, generically at least, to appear already at one loop. And so, if you study the UV behavior in these theories, you can generate a lot of data which may help you understand the UV behavior in general gravitational theories. So, having said that, there's already a difficulty in this, in analyzing these theories of reduced supersymmetry, which is the following. Supersymmetry, when you have n equal to 4 or more, is sufficient so that to specify the theory completely, to know what theory you are talking about, it is sufficient just to tell the amount of supersymmetry and the matter content, the number of vector multiplets. This is not the case for n equal to 2 theories. Over there, you can have 2 theories with exactly the same spectra, but different interactions still preserve n equal to 2 supersymmetry in 5 and 4 dimensions. So to understand what theories you're talking about specifically, you should be able, you must look at the Lagrangian of the theories, really. Now, if you want to do perturbation theory with this Lagrangian here, this is an extremely complicated task. For the following reason, you have, for example, that there are these matrices which appear in the kinetic term for vectors and scalars, but these are really non-polynomial functions of the scalar field in your theory. So that means that this theory has an infinite number of interaction vertices. Doing perturbation theory brute force to this theory, it is something very, very hard. However, there is a dramatic simplification, which happens in n equal to 2 theories which do exist in 5 dimensions and are of the Maxwell-Einstein class, that is no hypermultiplets. So all quantities of the Lagrangians for these theories are specified in terms of a symmetric tensor, the C tensor, which appears in these very characteristic cubic couplings. These are F-wedge couplings, which are regulated by this tensor. This tensor carries 3 symmetric indices which run over the number of vector fields in your theory. Okay. Once you know the C tensor, it has been shown by Murat and friends that you can reconstruct the Lagrangian unambiguously at all orders. The construction goes as follows. You are starting by introducing a fictitious ambient space with coordinate psi. This ambient space has a dimensionality equal to a number of vectors in the theory in 5 dimensions. And then you are associating to this C tensor a cubic polynomial in this ambient space, defined as here. And then you have that all the quantities which appear in the Lagrangian, including also the fermionic part, which is not displayed here, have a simple and straightforward geometrical interpretation in terms of this ambient space with this structure. For example, the target space of the theory will be the hypersurface in which this cubic polynomial is equal to 1 in the ambient space. This ambient space is endowed with a metric, and then you'll have that the restriction of the metric on the target space will give you the matrix A, which appears here for the vectors, for example. So we started from a very complicated problem, which is writing down Lagrangian with n equal to 2 supersymmetries in 5 dimensions, and we ended up with a considerably simpler problem, which is studying cubic polynomials in a given ambient space. Not only that, but the theory is uniquely specified by cubic interactions, because by looking at cubic interaction between 3 vectors in 5 dimensions, I can read off the C tensor. So from the point of view of an amplitude practitioner, what is really critical about these theories is that sufficient knowledge of 3-point amplitudes specifies the theory completely. Okay, having said that, the next step after writing down the theories in 5 dimensions is to reduce the theories down to 4 dimensions. So what do we get in 4 dimensions? Now this is my schematic rendition of the space of theories in 4 dimensions I'm interested in. This is my panoramic view, so the simplest theories, I put them here. These are theories with a lot of symmetry. These are symmetric spaces. They have symmetric spaces as a scalar manifold. It turns out that there are only an infinite family of theories, which is sometimes named generic Jordan family, because the theory of Jordan algebra was used in writing down the corresponding cubic polynomials. Then there are 4 exceptional cases, which are so exceptional that they are named magical theories or magical supergravities. Turns out there is a connection between these 4 theories and division algebras. And these are the simplest theories which fit into this class. Now, one thing you can do if you want slightly more complicated theories is to consider theories which do not have symmetric target spaces but have homogeneous manifold as target spaces. And here there is a classification of these theories, which is due to Van Promen and DeWitt, which is quite important for what I am about to discuss. Also, you can consider theories for which most of the entries of the C tensor are generic. This is one thing you can do. Another thing you can do is to generate theories which are of the Yang-Mills Einstein kind, through gauging. The theories that are represented here are Maxwell-Einstein. There is no abelian gauge interaction in these theories. But you can promote some of the isometry group to gauge group, and in that particular case you end up with Yang-Mills Einstein theories. Or if you decide to promote some of their symmetry to gauge symmetry, then you end up with proper gauge supergravities. We will focus to the first class of theories here, and particularly compact gauge groups. A feature these theories have is that they always admit Minkowski vacuum, which is good from a point of view of amplitudes, because, well, amplitudes make sense with Minkowski vacuum. Having introduced then non-abelian gauge interactions, a very natural thing to do is to break them through the Higgs mechanism. So what I want to do in the next 15 minutes is to take you around this fictional schematic space of theories with the double copy. So I want to explain to you what you need to do to go from ear to ear, from the point of view of the double copy, from ear to ear, and from ear to ear. Okay? Let me provide you a little bit more details about this generic Jordan family, which is here our starting point, this adventure in theory space. So the prepotential is written here, the cubic polynomials. You can see it has a very simple form. And then, for example, you may want to consider theories which have homogeneous target spaces. You look at the prepotential written here by the Witt and Van Proyen, and you see that a sector of the theory is exactly identical to the one you have for the generic Jordan family. To go to homogeneous target spaces, you have to add some extra stuff, namely some extra vector multiplets, which are these xi's corresponding to Greek indices. When you do so, you have that some of the entries of the C tensors are gamma matrices. They form a representation of a Clifford algebra with a given dimensionality. And the result by the Witt and Van Proyen is that all homogeneous supergravities fit into this form. So the problem of classifying homogeneous supergravities has been reduced to the problem of classifying representation of a Clifford algebra with a given dimensionality. You will have that the number of these Greek coordinates in particular is a multiple of the dimension of the rep of the Clifford algebra for that particular value of Q. Okay. When you have a number of Greek coordinates larger than the one of the rep, then you have some additional symmetry in the theory. And again, we will try to recover this structure, Clifford algebra, and then these extra symmetry groups, from the point of view of the double copy. So having said that, the question which comes is here, what freedom do I have in the double copy construction which can allow me to move around in the space of possible theories? Okay, and the freedom is the following, and I start from a general statement and then I provide particular examples of this. The freedom is that we can introduce gauge group meta representations, that is, representations other than the adjoint in the gauge theory. More formally, what we do is to divide the spectrum of the gauge theory into an adjoint sector, and then sectors correspond to matter representations. And we declare that supergravity states are associated to gauge invariant bilinears made of states from the two gauge theories, so that states in the adjoint go with the adjoint, and states in a matter representation go with the conjugate representation. What kind of color factors can you build? Well, you will build your color factors out of the structure constant, but also the representation matrices, and in some cases, Clebsch-Gordan coefficients. And you will have that Jacobi relations, but also commutation relation between the representation matrices, and also relations involving the Clebsch-Gordans in some cases, produce color identities. These color identities then need to be visited upon the corresponding numerator factors to have a representation of the gauge theory amplitude, which you can use for double copy. Very good. So let me provide the first example about this. This is our starting point, which is the generic Jordan family. The theory there, which enter the double copy construction, are an n-equal to 2 super-Yang-Mills theory with no additional matter. Not much happens here. The whole point of this gauge theory factor is to have enough supersymmetry in the resulting supergravity. Then we consider non-supersymmetric Yang-Mills scalar theory, such that this is really a higher dimensional Yang-Mills theory reduced down to 4 dimensions. This is essentially the first line here, I write down. And then, after writing this, I realized there is already a very natural coupling or deformation of the theory I can consider, which is trilinear scalar terms, interaction terms. These terms will be regulated, will be controlled by a tensor, which is antisymmetric in 3 global indices of the scalars, this F tensor. The tensor is put in the theory as unconstrained, but then you want the theory to obey color kinematics duality. You look at amplitude with 4 scalars, and it comes out that this F tensor is to obey its own set of Jacobi relations. So it should be thought of as the structure constant of some group. Now you double copy, and you're getting that the supergravity field are obtained in the following way. You have I mean, I said before, this is just a joint times a joint double copy. We will see more complicated examples. And you have, for example, that some of the vector fields are obtained as a vector in the n equal to 0 theory times scale the n equal to 2, and some the other way around. You may wonder what is the effect of having those trilinear couplings, which we were discussing in the non-supersymmetric gauge theory. You see that those trilinear couplings turn on this amplitude between 3 vector fields. But then, looking at this amplitude, you realize really that this is a smoking gun signature of having a Yang-Mills Einstein theory as opposed to a Maxwell-Einstein theory, in the sense that you are having 3 vectors interacting. This is really a non-abelian gauge interaction. Not only that, but you have the this tensor, which appears in those trilinear couplings in the gauge theory, gets promoted essentially to the structure constant of the gauge group of the supergravity. And so something quite interesting has happened here, because we started from a global symmetry in one of the gauge theories, and we have promoted that to a gauge symmetry through the double copy construction in the resulting supergravity. So I would like next to modify this construction just a little bit so that we can cover homogeneous supergravities. The minimal thing I can do from the point of view of the gauge theory of supersymmetry n equal to 2 is to add the smallest possible number of states. This corresponds to an alpha hypermultiplet, which preserves n equal to 2 supersymmetry, and it is a CPT self-conjugate, provided that you take that to be in a pseudo-real representation of the gauge group. Now, as the other gauge theory, we will consider essentially the theory we wrote before, and then we will add the fermions. And we will allow the fermions to partake Yukawa interactions with the scalars of it. Once more, we have here a tensor with global indices from the point of view of the gauge theory, and we are asking color kinematics duality to constrain the tensor for us. Color kinematics duality comes back and tells us that the tensor needs to obey a Clifford algebra, therefore these are gamma matrices. So already we are uncovering that Clifford algebra structure, which was essential in classifying homogeneous supergravities a la Van Proyen and DeWitt. Not only that, but we know that the theory really exists in higher dimensions, because due to the fact that these tensors are gamma matrices, you can uplift it to Q plus 6 dimensions. Or this parameter Q counts the number of scalars in the theory. We are back in a situation which is very much alike a textbook treatment. We have one of such constructions, one of construction of this class. To specify it completely, we need just to tell you what dimension we are operating, and then to add a certain number of irreducible spinors in that dimension. So we are back to a textbook treatment of irreducible spinor in d dimensions. There is only one twist, which changes some of the numbers in the table. That is that the reducibility conditions on these spinors, there's going to be some reality and some pseudo-reality conditions. They involve a matrix V, which is the matrix entering in the pseudo-reality condition for the gauge group representation in which this fermion is transformed. So this is the only deviation from the textbook treatment of this. And when we have more than one irreducible spinor, we have an extra flavor group. And the surprise, we reproduce essentially the same table which DeWitt and Van Proyen had previously written down for homogeneous supergravities. Now, let's have a look at the supergravity states which come about in the double copy construction. There is once more an adjoint times adjoint sector here, and then there's an additional stuff coming as the double copy of matter representation states in the two-gauge theories. This will be the additional vector multiplets which I pointed out in discussing the homogeneous supergravities from the point of view of the cubic polynomial. Now perhaps let me highlight a couple of features about a more drastic example of this idea of introducing extra matter representations. We want to do spontaneously broken supergravities, and we want to introduce a different matter representation for each mass in the spectrum of the supergravity which we are trying to reproduce. We take as one of the gauge theory factors a spontaneously broken super-Yamil's theory, which is a spontaneously broken version of the gauge theory which we used in the previous constructions. In this particular case, schematically, we will have extra color identities. There will be color factors which involve representation matrices and also Church-Gordon coefficients. And we will have extra color identities which stem from the fact that the matter representation in which the W's, for example, transform, are not arbitrary matter representation, but they must come from the symmetry breaking of a larger gauge group. Once we have done this and classified the color relations, what we need to do is just come up with another gauge theory, which we take as an enhancement of the previous gauge theories. This is a Yamil's scalar theory with extra massive scalars and trilinear interactions. And then we impose the numerator relations corresponding to the color relation of the other gauge theories on this theory. The final point is a construction which reproduces the amplitudes of spontaneously broken supergravities, and once more you have adjoint times adjoint double copies which give you massless fields, and then you have matter times matter double copies which give you massive vector multiplets here with W's and scalars in it. These are just, of course, the Poisson multiplets. So in the last couple of minutes, I would like to present a couple of highlights about going to one loop, because so far we have done everything at tree level. I will be very schematic here, but I can tell right away that there are some amplitudes here which are very simple at one loop. This will be matter amplitudes from the point of view of the supergravity, which the vectors are made as fermion times fermion in the two gauge theories. There is a fundamental property from the point of view of the BCJ numerators which appear in the representation for the n equal to 2 gauge theory. That is, the numerators do not have explicit dependence on the loop momentum. You have boxes, you have triangles, you have bubbles, but you have no explicit dependence on the loop momentum. The consequence of this is that you can see a direct link between the UV divergence in the supergravity and a combination of one loop corrections to vertices and propagators in the n equal to 0 in the other gauge theory, the one which is non-supersymmetric. This is a structure actually very similar to what you see in computing, for example, a beta function. Not only that, but you can, for example, consider a particular case in which you have two identical vectors and distributed conjugate states. And you can write down your divergence as a function of the parameters in your theory, namely the number of scalars and the number of fermions in your theory. So, let me just summarize what I've left. This is my executive summary of n equal to 2 times n equal to 0 double copies. Our starting point was this construction for the generic Jordan family. And what I try to persuade you of is that there's a simple sequence of operations which you can do. It's a very natural deformation. For example, linear coupling is one of the theories. And whenever you find something natural, something meaningful to do to the gauge theory factors which enter this construction, there is something equally natural, but a priori quite different, which happens from the point of view of the supergravity theories. And everything keeps working like a charm. So to conclude, the double copy extension which we have done so far, they also have a strategic value in the sense that they are gateways or stepping stones for doing even more general extensions. An example of this is the spontaneously broken supergravity construction. which is technically just a Coulomb branch. This is a prerequisite if you want to do, for example, R-symmetry gaugings with Minkowski vacuum. So both the fact that the strategic value of these extensions and the fact that we have already found so many double copy extensions seems to point that this construction has an important role to play in the big picture for theories of radius supersymmetry. I should also mention that everything I said is about n equal to 2 gauge theories, but you can replace the n equal to 2 gauge theory, which in some cases we're just going around for the ride to provide you enough supersymmetry, with a gauge theory, we have another gauge theory factor with n equal to 4 or non-supersymmetric. In that particular case, you end up having supergravities with different, of course, amount of supersymmetry, but the construction, the general implant of the construction still works. And finally, it should be mentioned that, as I was showing before, these computations that one do find hints of simple structure. So it seems very feasible to go to higher loop or higher point. And this concludes my presentation.
I was just trying to understand this statement. So the part that's going along for the ride,
yes.
Could you just replace that with just the gauge theory and n equals 0 gauge theory?
N equal to zero gauge theory. Well, so what makes more sense to replace it with is we have a truncation of the n equal to 2 theory, which is an n equal to 0 theory, gauge theory plus scalars.
Oh, okay, so
because, for example, you would have, I mean, it's a case-by-case situation, okay? But, for example, how do you go on the Coulomb branch if you don't have scalars, right? So there's a natural n equal to 0 candidate for replacement, which is throw away the fermions, and that's what you have. The n equal to 4 theory also, you can use that in everything except the homogeneous construction, because you need the hypermultiplets, and n equal to 4 hypermultiplets, they're not there.
So how does introducing higher derivative terms modify your prescription?
Higher derivative terms, you mean higher dimensional operators in the gauge theory? Or
Supergravity, such as r squared and r squared f to the 3p minus 2.
Oh, okay. So this is something which, so first of all, this is a very interesting, I want to say open question. So there's been some work done by Johannes Brodel and Dixon, and introducing, seeing higher dimensional operators from the point of view of the double copy. In these particular constructions, I have not tried yet putting higher dimensional operators.
Right.
But this
The reason I mention that is because those coupling are constrained by the VCOV and AVI equations. So it would be interesting to understand those equations from this double copy point of view. From
yes. Yes, that's a true statement.
So in your Higgs case, can you break the gauge symmetry completely such that you only have massive vector bosons in the theory? And if that's possible, what's a double copy?
Sorry, what's the last part of the question?
If that's possible, if BCJ is possible, what's a double copy?
Oh, so, okay. Okay, very good. So, the work which we have done on the spontaneous symmetry breaking is something which should apply to arbitrary symmetry breaking patterns. So you can break it down just for a sequence of U1s. Now, as what happens for the double copy, well, you have a very important freedom which is left, that is to specify the other gauge theory which enters the double copy. All you know about that gauge theory is that it should have essentially the same spectrum, I mean the same masses and the same conjugate gauge group representations. So if you do this with what we have done, you would just end up having a spontaneously broken supergravity which is broken down completely. Because what we have double copied that theory with is just a theory with scalars. Massless scalars and then some massive scalars which pair up with the W's. Now another interesting question is what happens if you take two of such theories together, two spontaneously broken theories together. This is something which is not 100% clear, but what we believe is that in that particular case you end up generating something which includes Kaluza-Klein states from a higher dimension supergravity reduced down in one dimension. I can provide more details private to them.
Any other questions? Not, let's think about that.